Hello there, my name is Eray Ozkural. I'm going to talk about abstract representations and generalized frequent pattern discovery today. Frequent pattern discovery is a costly subproblem in association rule mining and related problems. Association rule mining was the initial problem that kick-started the data mining field. Some examples of frequent pattern discovery are items and sets, subtrees and trees, subgraphs and graphs, subimages and images. That is to say, we can define a pattern discovery task in a lot of data structures. AI unification research, as Alexei Potapov explained, is about finding a common theoretical language to express everything in AI. Here we are trying to generalize a common task in data mining using information theory. The goal is to make a universal data mining API that is independent of the data type and has very few parameters, which is also called parameter-free data mining. Some tasks that I'm trying to put together are summarizing binary data, finding frequent patterns among them, scalable binary data classification and clustering, again independent of the data, works on binary files, and a binary data similarity graph construction. So these are some common tasks in data mining, and we're trying to generalize them. Frequent pattern mining works on a database of bit strings here, and we use a support threshold epsilon, and we find all bit strings p that occur in T with frequency that is greater than the support threshold. So this would be the bit string generalization of frequent item set mining. And frequent item set mining has an important pruning lemma called the downward closure lemma, which says that all subsets of a frequent item set are frequent. Here's an abstract pattern model to make sense of approximate pattern matching. A is an abstract representation of B if and only if A is substantially less complex than B, as we're losing some information, and every important feature of A is similar to an important feature of B. We can try a mutual information approach for formalizing condition 2. Here's an attempt at an abstract pattern model using AIT, which is supposed to work with our bitstring generalization of frequent item set mining. A transaction set T is again a database of bitstrings, and patterns X and Y are also bitstrings. An abstract pattern X occurs approximately in Y if and only if the algorithmic complexity of X is sufficiently reduced with respect to that of Y, and the conditional algorithmic complexity of X given Y is sufficiently small with respect to that of Y. Here, C1 and C2 are between 0 and 1, and C2 is smaller than C1. The figure explains what this means. Here, as you can see, h of x is a lot smaller than h of y. In most cases, it is probably going to be like this. And there's a gap between C2 and C1, and that corresponds to the noise in the abstract pattern X relative to Y. So the noise is the extra algorithmic information we need to construct X given Y. But as you can see, there's a lot of mutual information between X and Y, which is to say the second condition is actually the pattern containment condition. but in a lossy way. And note also that this isn't a great way to use lossy compression. It wasn't intended for exactly that. There are a lot of ways to define an abstract pattern relation, of course. This isn't likely the ideal one, but we're looking for it. The logical next question to ask, given the abstract pattern model of the previous slides, is whether we can obtain a general pruning theorem like in data mining research. It turns out there is one, which is like the contrapositive of downward closure lemma. It's quite simple. It says that any extension of an infrequent pattern is also infrequent. If X is infrequent, then either condition does not hold. Any extension xz violates either condition. Entropy in the left-hand side of the condition would grow, and this fact does not apply to null patterns, so you can't use it in the basis. Based on these observations, I designed an algorithm to synthesize abstract patterns. The algorithm is called microsynthetic. It's not supposed to work on realistic use cases. It's just a proof of concept. It does not scale much, hence the name micro. We approximate algorithmic complexity H, which is undecidable, by a practical compressor C, like the well-known gzip, bzip2, or PAQ8F compressors, all of which we use in this implementation. We conduct breadth-first search in pattern space like a priori does. We start with n-bit patterns, and then we detect the frequent ones. We count the frequencies, and we then prune the generated set, and then we extend those frequent patterns by n bits at the next level, continuing a breadth-first pattern search. Admittedly, this work is quite limited, but it was still hard to fit it in 10 pages. I think that there's a lot of future work to be done here. First, I think this should be extended to a lossy compression model properly, and then maybe we will find more interesting relations. We should be able to reason about probabilistic patterns, because that will be more practical compared to approximate patterns, of which there are many. Can this formalization address deep models? Theoretically, since a subnet of a neural network is like a subprogram, this might explain something about deep learning. This relation might be investigated. And the next obvious thing to do is to design a scalable algorithm that will work in program space rather than pattern space. And we might be able to find more pruning theorems, and this would help scalability more. There's a reference implementation. If you follow the link, there's something on GitHub. It currently uses PAQ8F, but bzip2 seems to work better on text data sets, which are the ones in the implementation. And this is, again, not meant for practical cases. You should take a look at the sample data. Thank you very much for listening. This is an exploratory work, and so far I have done little. But a lot more has been planned, and I'm hoping that you will find this direction interesting. And thanks to the reviewers for the extraordinarily helpful reviews, which did help improve the paper and fix an important error. Please send any questions to examachine@gmail.com. I'm looking forward to your mails. See you around.